Welcome. How do you pronounce your first name?
Mehdi.
Mehdi. Okay. I was gonna say Mehdi. Mehdi. Okay. Good to see you, Mehdi.
That's perfect.
Yeah. Thank you so much for agreeing to give a talk. Yeah. So this series has been fantastic in terms of understanding the nematic phase in the barium nickel to arsenic 2, because this is one of the key areas we want to have a deeper understanding.
Yeah, no, that's super nice. So usually I watch the seminar online afterwards because it's already a bit late in Germany.
I don't know. I'm sorry, you have to give a talk so late.
No, but I mean, I really enjoy to watch all these talks. So so it's really a pleasure to give one. Yeah,
it's great. Yeah. So we're actually doing in-elastic neutron scattering on this at the moment, trying to figure out what's going on.
Okay, no, that's very interesting.
Yeah. I mean, there's maybe some phonon softening and something like that. I don't know. Yeah.
Okay. Yeah, there have been some recent paper of inelastic X-ray scattering.
Right. Yeah, that's what was from one of my former students.
Ah, okay.
That's the problem, right? If you graduate really good student, they compete with you.
Yeah. That could be a problem.
No, that's okay. I'm very happy for him. Yeah, Yusong, he's very good student. Yeah.
Well.
So do you want to try it? Do you want to try to upload your stuff?
Yeah.
Whether you can share screen and so on and so forth. Yeah.
That's a good idea. Okay.
That looks very, very good.
Okay.
Oh, you have the wrong view.
What should I do?
You should switch terminal. We have your presenting view. So you must have two terminals, right?
Yeah.
Yeah. So you should switch the monitor. There's a button there saying switch the monitor.
Okay.
Yeah, this is okay, but this is not the presenter view. Yeah, you want to from beginning.
If I just do like that, I know.
No, yeah, then we're seeing you. Yeah, there's a terminal there. That's okay. Yes, just keep it there.
Yeah.
There's a button. There's a terminal there. Just say from the current slide.
Okay. From the current slide.
Yeah.
Okay. Seems to be okay.
No. We're just seeing it's not the presenter view. Yeah. You want to try again?
Yeah. So what should I do? Like
just do what you did before. Just switch the monitor. The two monitors, right? Just switch the monitor.
Yeah.
Oh, this is good. I think this is good.
Okay.
This is good. Perfect.
Okay, super.
Perfect. Hey, Jeff. Good to see you.
Hey, how you doing?
Good. Yeah. How are you doing? Yeah. Thank you for joining us. It's interesting.
Sure.
This is interesting material. This is the only material I know of. It doesn't have magnetism yet, still displays the so-called nematic phase. That's why I'm very intrigued by this material. Yeah. So it's really, really interesting. But we'll try to learn more about this.
Ken Chang, you told me once that you searched desperately for magnetism in this material.
Yeah. No, we found none.
Did you ever publish this?
No, actually, this was the days. This was the days when I was young.
That's a song, I believe.
Yeah.
No, yeah, this was when Leland was a graduate student with me. He's now at NIST for more than 10 years. Yeah, no, we never published it. No, I mean, it's tough to publish a paper when you don't see anything, right? I mean, as you know,
right.
You just tell people that you looked, there was nothing there.
But now you can say that
people are not going to be very happy, right?
Yeah.
Yeah. No, we never published anything. No, yeah. I wish we actually did. We put on the spectrometer. We spent a week. We keep looking, and then there was nothing there. We decided that was the end of that. Yeah.
Well, because I know we've in several papers we've probably wanted to cite something, but I think the only paper we can cite is Athena's paper.
Yeah, but it's very tough to publish a negative result paper,
Right.
I mean,
just put it on archive. It's easy.
Yeah.
It's the same as publication, right? People will accuse you.
It will get cited, guaranteed.
Yeah.
Yeah.
You can just cite them as private communication.
Wow, you don't have to cite me. I don't need one more citation from JP.
Or just as a well-known fact. It doesn't even need to be cited.
Yeah. People. This stuff really does not have magnetism. We worked very hard trying to look for magnetism. We just found none. Yeah. So I mean, what time is it? Oh, it's already okay. Yeah. So okay. So welcome everyone. Yeah. So people are continue to join in. So we're extremely happy to have Mehdi Frachet.
Yeah.
Frachet. Yeah, did I pronounce correctly? Yeah.
Yeah.
to give a talk. We have actually quite a few talks in the series, starting from JP, the very first talk to try to understand barium nickel 2 arsenic 2. The reason I think this class of material is extremely interesting is because this is the only system that I think I know of that has no magnetism, yet it may potentially display this very interesting nematic phase. It is critically important to understand, where this nematic phase or potential nematic phase is coming from, and where this, lattice distortion and charge ordering is coming from. So yeah, so we have quite a few on this series already, and we have the sort of probably the final one on this. Yeah, so welcome. Yeah, please, it's all yours.
Thank you, Pencheng Dai. So that's my pleasure today to present our recent elastoresistance experiment in this phosphorus doped barium nickel arsenide. So as I said, that's really a pleasure to be part of this to present this seminar. So I really enjoyed the last few talks. So that's really nice. So as I said today, my focus will be the elastoresistance. But I will also give a few words of the work of Christoph Meingast at our institute that did with his co-workers a very detailed thermodynamic study of this phosphorus doped barium nickel arsenide. Okay, so let me first start by acknowledging many people that work on this system at our institute. So the Institute for Quantum Materials and Technology in Karlsruhe in Germany. So I'm Yari Gira, Tom Lackman for the crystal growth. Tom was also involved in the spectroscopic experiment that Mathieu Lecatacon described 2 weeks ago. So that was also work of Michael Merz, CIAO, Michael Assoulio. So for the thermodynamic part, I would give a few words about this. So this was done by Christoph Meingast, Liran Wang, Christine Villa, Frédéric Hardy, and Mal Shukla. I would like also to thank Roland Villa, Igor Vinograd for discussion, and for the transport and elastotransport experiment, Anna Bomer and Paul Vicky. Okay, so my talk is divided in 5 small parts. I hope small enough. So the first one is an introduction. I would like to explain why barium nickel 2 arsenic 2 is an interesting system, and what do we want to learn from the system. Okay, so there is many reasons that this system is actually interesting, but one of them is because it could possibly be an electronic nematic system. So let me just define what it means in a few words. So a nematic state of matter is a state where the translational symmetry is preserved, but there is a rotational symmetry breaking. So just like on this sketch. So what we are really interested about is not only nematicity, but electronic nematicity, when the rotational symmetry breaking is induced, driven by an electronic degrees of freedom, like spin, charge, or orbital. So that's not so easy actually to say that a system is an electronic nematic system, because as you know, as soon as the rotational symmetry of the crystal lattice is broken, you also have anisotropies that emerges in the spin, charge, and orbital electronics degrees of freedom. So there is one way to deal with that problem, which has been used quite extensively, I would say, in the case of iron-based superconductors, which is to look at the electronic nematic susceptibility above the symmetry breaking. And there are different ways to do that experimentally, but one of them, and that's the focus of this talk, is the elastoresistance measurement. So I'm just showing you this paper from Gino Shu and the group of Jan Fischer in Stanford. This was already done 10 years ago, in this barium iron 2 arsenic 2. And what they did in this really beautiful experiment is to measure actually the resistance anisotropy induced by anisotropic strain above the nematic transition. And what is really nice about this resistance anisotropy is that under certain circumstances, it's a good proxy to the electronic nematic order parameter. So what they did is to study the response to strain in the elastic limit, and they extract this M66 elastoresistance coefficient that belongs to this B2G symmetry in the tetragonal state. And this elasto coefficient is directly related to the electronic nematic susceptibility. And you see this very beautiful Curie-wise behavior that extend well above the nematic transition. Okay. So electronic nematicity is, I would say, an exotic electronic state of matter, which is interesting in itself. But what makes it even more interesting is, at least to me, its interplay with superconductivity, at least in some compounds. So you have an example of this cobalt-doped barium iron arsenide. So that's again a paper from the Jan Fischer group. And you see that so the color code is actually the strength of the nematic fluctuations, again in this B2G channel. And close to the optimal condition for superconductivity, you see that there is strong nematic fluctuations, okay, which suggests that such fluctuations could enhance the superconducting pairing. So now the question that follows is, what is the mechanism behind this electronic nematicity, sorry. And so the consensus or most evidence point to a spin-driven mechanism, at least in some ion-based superconductor. And one manifestation of this is, you know, the proximity of this long-range magnetic order, this stripe magnetism. Okay, so what we are interested about is, you know, other way to electronic nematicity, other way than this spin-driven mechanism. And there have been actually quite a lot of study in different types of compound looking for electronic nematicity. For example, in copper oxide, in cuprates, but also even in this new Kagome superconductor, which has been recently found. Okay, but so far, I would say that we are still looking for a clear example of charge orbital driven electronic nematicity. So that we have not found yet, I think. And that's particularly interesting because, as you know, in many unconventional superconductors, there is, for example, charge and wave instabilities. Okay, so that's now that our barium nickel 2 arsenic 2 is interesting. So that's our candidate for this type of nematicity. So a few things to mention. That's a compound which is isostructural to barium iron 2 arsenic 2. It has the same structure, tetragonal structure at high temperature. But so far, there is no evidence for long-range magnetic order. Okay. If you look to the resistance as a function of temperature, you see close to 135 Kelvin, this strong first-order transition, which actually signals a change in the crystal structure. And the low temperature crystal structure is triclinic, which is the lowest symmetry you can get from tetragonal. That's also already a superconductor. So at quite low temperature, 0.6, 0.7 Kelvin, and you see this nice specific heat data, thermal conductivity. You see there is no residual thermal conductivity at low temperature, so it's a fully gapped superconductor. Okay, so no long-range magnetic order, but what makes this compound even more interesting is the discovery of several charge density waves a few years ago by the group of Peter Abamonte. So what they discover exactly is that upon cooling in this tetragonal phase, there is first an incommensurate charge density wave that develops. It's enhance strongly below a given temperature of 155, 60 Kelvin. Okay, and this incommensurate wave, there is two modulation along the x and y axis, but the same modulation along the two axes. And you see that it's enhanced and then it's suppressed when you go into the technique phase. And there is another charge density wave that develops at the expense of this one, which is commensurate and uniaxial. Okay, so another very interesting and important result in this compound was obtained in this strontium-doped barium nickel.
Do you mind if I stop you?
Yeah, please.
Could you go back to the previous slide? I
Yes.
missed the JP's talk earlier in the series. So
Yeah.
So is this in the, I guess you label this in tetragonal notation. So this is the incommensurate wave vector is within the tetragonal plane. Is that?
For this one, yes. I think for this one, actually, I make a mistake. So it should be triclinic. It's in triclinic notation.
That's the wave vector in the triclinic.
Yeah.
That is okay. Thank you. Yeah.
Sorry. So to come back to this this slide. So this very important result in strontium doped barium nickel 2 arsenic 2, which was obtained 2 years ago by the group of John Pierre Paglione. And what they did is that they studied the complete series from the barium side to the strontium side. And first, two things to notice, you see that using strontium, what they could actually do is to completely suppress the triclinic structure. And you see that just when this triclinic structure is suppressed, you have a sharp increase in TC that goes up to something like 3.5 Kelvin. So that's an elastoresistance study. And what is very important, what they uncover is actually that this material has a very large B1G symmetric elastoresistance. So that's really not a subtle effect. It's of the same amplitude as in barium iron 2 arsenic 2, for example. And what is also important is that, close to this doping of 75% of strontium, the elastoresistance in the B1G channel has this nice Curie-Weiss temperature dependence, and the associated B1G nematic fluctuations are actually the best candidate that we have so far to explain this six-fold increase of TC from the fully strontium side. Okay.
But there's no charge ordering, right? I mean, in this particular sample, right?
No.
Sample, according to JP, there's no charge ordering, right? JP can confirm.
I think so far there is no charge order which has been found there. Yeah, I think that's a good point. Yeah.
Thank you.
So what we studied is this phosphorus doped barium nickel arsenide. So you see it has some similarities with the strontium sample which I showed you just before. So with phosphorus doping, we are also able to suppress the triclinic phase. And you see when we suppress the triclinic phase, there is a first order like increase in TC, which was already reported a few years ago by Kudo et al. Okay, so that's the similarity. The difference with the strontium sample material that I showed you before is that you see on the phosphorus side, on the overdope side, you see that TC is quite flat as a function of phosphorus substitution. So the first question that I would like to ask now is how evolves the B1G elastoresistance in this slightly different system, and I will ask more questions during this talk actually. Okay, so I would like to start to show you some data, but not starting by elastoresistance, but by the discovery of another structure in this material, which is this orthorhombic structure, which was reported a few, I think 1 or 2 years ago by Christoph Meingast and Michael Merz. Okay, so you have already seen this figure a few times. That's high resolution thermal expansion in this undoped barium nickel 2 arsenic 2. So thermal expansion as a function of temperature, and you can see thermal expansion along the 100 axis in red, along the 110 axis in black. And what we can notice together is that you see that the thermal expansion is really the same along these two directions down to something like 145 Kelvin. But below that temperature, there is a clear difference between these two directions, which indicates actually that there is a breaking of the rotational symmetry. So what actually occurs below 145 Kelvin in this orthorhombic state is that when the sample is aligned along the 100 axis, okay, using the thermal expansion setup, you apply a tiny force which allows to detwin the sample. So you measure the smaller in-plane axis. Now, when the sample is aligned along the 110 direction, you still measure a combination of the two in-plane direction. So there is no detwining effect. Okay. So that's what occurs in this orthorhombic phase in thermal expansion. Okay, so now to come back to this figure that you have already seen, what it means that you see just below this strong enhancement of the incommensurate challenge wave, you have this second order phase transition at about 145 Kelvin, which corresponds to a B1G, that is distortion. Okay. Now, Christoph Meingast has also studied the evolution of this orthorhombic distortion with phosphorus substitution, and I'm showing you an example at 5%. You see that the orthorhombic distortion as a function of temperature. You can see that the transition now is close to 100 Kelvin, so it's already quite substantially shifted to lower temperature. And what I want you to look is actually the amplitude of the orthorhombic distortion. That's super small. That's like 1 order of magnitude smaller than in barium iron 2 arsenic 2. Okay. What you can see on the lower panel is actually also a specific heat, a tiny specific heat anomaly, which is associated to this second order transition. Okay. So one point I would like to make is just to mention that it's actually not so easy to compare the amplitude of the orthorhombic distortion for different phosphorus substitution, and the reason for it is that you measure this distortion until you go into the trickling phase, and so the temperature range that you have for this orthorhombic distortion to develop, especially in the undoped compound, is super small, like just a few Kelvin. Okay, so it makes things a bit complicated to compare, and that's why this orthorhombic distortion looks very small in the undoped compound. So Christoph Meingast sent me this nice plot actually, so that the orthorhombic distortion as a function of phosphorus content. And what you can see, what he did actually is just to extrapolate this orthorhombic distortion to lower temperature in the undoped compound as if there was no triclinic transition. And what you can see is that actually what it suggests is that the amplitude of the orthorhombic distortion is not that doping dependent. It seems to be rather constant as a function of doping.
So let me ask you a question. So in the case of barium 122, you see this orthorhombic distortion sort of has the Curie West temperature dependence, right? Here, what you found is that it really seems like a truly second order phase transition, right? Because in the case of barium 122, you have this structural distortion above the structural distortion, like Junhao has seen the clearly, MR effect, the transport measurement shows clearly Curie West temperature dependence, and you guys see the same thing. But here, it's clearly, it's like you say, the heat capacity as well. Shows really, it's actually a phase transition. So it's really, you cannot say this is a fluctuation regime, right? This is not really a fluctuation regime, right?
I don't think we can say so. Yeah, I will show you the elastoresistance that we get in this undoped compound also. You will see it's also quite sharp.
Okay, thank you. Yeah.
Can I ask?
Yes.
Sorry, keep on asking the same question. Do you mind going back to the previous slide, please?
Yes.
So you have QX and QY. Is that the ion bond direction, or this the nickel bond direction, or this is the arsenic direction? When you say X and Y.
I'm not sure.
Okay. Well, we'll follow up.
I think it's nickel, but I could be wrong, so I don't want to.
Thank you.
So this orthorhombic distortion lead us to revise the phase diagram of this this phosphorus doped barium nickel arsenide. So that's what we get now. So you see, upon cooling, what we first get is this strong increase in the intensity of the incommensurate charge wave. At slightly lower temperature, you have this second-order orthorhombic transition. And at even lower temperature, you have this first-order trichinic transition with this commensurate charge wave. At very low temperature, there is this superconducting phase, and you see that there is this strong increase in superconductivity in first-order lag fashion from 0.7 to something a bit above 3 Kelvin. I think it's 325 or something like that. Okay, so there are new questions that comes with this orthorhombic structure. I think the first one is whether this structure is actually a signature of charge-driven nematicity. That's one question. Second question is what actually occurred to the B1G elastoresistance at this orthorhombic transition temperature. And a third question, which we will try to reply in the following of the presentation, which is not directly related to this orthorhombic phase, is what is actually the origin of this superconducting increase at 7–8% of phosphorus doping. Okay, so let's first talk about the elastoresistance of this undoped barium nickel 2 arsenic 2. So we have used the same setup as was used already 10 years ago by Jan Fischer. So you see a simple piezoelectric device. The sample is glued on the top surface. There is a strain gauge on the back side, and it allows us to estimate the strain that we transmit to the sample. Okay. So I will show you data in this B1G geometry. So that means that the a-axis, the tetragonal a-axis of the sample, is aligned with the pulling direction of the piezo. And we can measure electrical resistance both along the pulling direction, but also perpendicular to it. And what I wanted to show you with this gold rectangles is the orientation of the electrical contact. Okay. So we measure the resistance anisotropy, we measure the strain, and so we can extract this M11 minus M12 elastoresistance coefficient that again belongs to this B1G geometry in the tetragonal phase. One thing I would like to mention, and that's important for the following, is that the thermal expansion of the piezoelectric device is actually anisotropic. So you can see this the thermal expansion of the device as a function of temperature, both along the pulling direction and perpendicular to it. So this was done by Christoph Meingast and Anna Böhmer. And you see that there is a difference. So what that means for us is that even if you don't apply any voltage to the piezo, you just glue a sample on top of the piezo and you cool it down. That means that you apply a bit of strain, and in particular, a bit of anisotropic strain, okay, even without applying any voltage. So on the right side, you have a figure with an estimation of the strain state for barium nickel 2 arsenic 2. So you have this anisotropic part, B1G, which is only due to the piezo. And you have this A1G part, which also depends on the thermal expansion of the sample, of course. Okay, so actually that's quite fortunate because it allowed us to extract to see a transport signature of the rotational symmetry breaking. So what you can see on this graph is resistance as a function of temperature of a barium nickel 2 arsenic 2 sample, which was glued to the piezo. And we measured electrical resistance in the two directions. So in black, you can see the resistance measured perpendicular to the pulling direction, and in red you can see the resistance measured along the pulling direction. So the field symbols are taken upon cooling, and the empty ones are taken upon warming. So what you can first see is that below this orthorhombic transition temperature, there is a clear difference between these two measurements, which means that the small anisotropic stress that we apply allow to, to detect the anisotropy of the resistance in the orthorhombic state. So I want to mention also there is this recent paper of RPES under uniaxial stress, where there is also a bit of electrical transport. So that's by Mingyi, Penchengdai, and co-workers. And they also observe resistance anisotropy above this treatment phase. Second thing I want to mention on this figure is that you see that there is a clear thermal hysteresis, which is an in-situ signature of the first order technique transition, so which allows us to pinpoint the technique transition on the piezo actually. Okay, so now let's apply some voltage and let's have a look to the data that we got. So that's transverse elastoresistance. So the electrical resistance is measured perpendicular to the pulling direction. Resistance as a function of strain, and you see that at high temperature there is not so much response to strain down to something like 165, 160 Kelvin. But below that temperature, there is a sharp response and quite large response actually that develops. And it's maximum close to 145, 46 Kelvin. And when we cool down further, you see that it weakens again. So a large elastoresistance that onset sharply close to a temperature of 160 Kelvin, and a maximum of the elastoresistance at this T star temperature, which is very, very close to the orthorhombic transition temperature. Okay, so one thing I would like to mention, so you see that there is an hysteresis in the resistance versus strain sweeps. So this is actually best seen at 130 Kelvin, that's what you can see on the right side. So this hysteresis was also observed in the strontium dope sample and in the undope sample as well. Okay, so this hysteresis onset below 150 Kelvin approximately, and it persists down to the lower temperature that we have measured. Okay, and I will come back to this hysteresis in more details when we investigate the doped samples. Okay, so what we usually do in this kind of experiment, that we just take the slope of this resistance versus strain variations. This is what is plotted on the right side as a function of temperature. So what you can see now is that we measure this upon cooling and warming, and you see that there is not so much difference actually between cooling and warming measurement. So same quantity, but in the longitudinal geometry, so measuring the resistance along the pulling direction, and you see that we see the same effect, but with an opposite sign actually. Okay. So just to summarize quickly, we have a maximum of elastoresistance in both channels, transverse and longitudinal, at this 145 Kelvin temperature. And we have similar cooling and warming elastoresistance, which is consistent with a second order phase transition. So we can start to complete our phase diagram with this T star temperature of the maximum of the elastoresistance. So I've just put it the first point. Okay, so from the data I just showed you, you can extract easily this M11 minus M12 elastoresistance coefficient. Again, it belongs to this V1G symmetry. So you take just the difference between the two curves I showed you before times some factor. And no surprise, you get this sharp peak close to the orthorhombic transition temperature. So what I think is very useful is to compare this actually to what we observe in barium, iron 2, arsenic 2. So that's not in this V1G channel, but in this in the B2G channel in the iron compound. So the M66 coefficient is the black diamond. Okay. And there is a few points which I would like to make with this this comparison. So the first one is that you see that the orthorhombic distortions that belongs to different symmetry channel in this nickel and iron compound occurs at quite close temperature. So that means that we can make a comparison. At the rotational symmetry breaking, so you cannot see it actually from the graph I have seen. So you need to trust me because I have scaled everything. But if you look to the raw data, let's say, you see that the elasto coefficient in the respective symmetry channel have quite the same magnitude. So really the amplitude of the effect is similar. But what is very different, and I think it's quite clear from this figure, is the temperature dependence, which is much sharper in the nickel compound, and in particular, it cannot be well reproduced by a Curie-Weiss fit, and this was also observed in this paper by Jean-Pierre Paglione and co-workers. So now, what I think is would be also.
Sorry, can I ask a question?
Yes, sure.
So just to be clear, this is for the x equals 0, right?
Yes.
Data you were showing?
Yeah.
So you're saying there's a peak in this this susceptibility at the orthorhombic transition.
Yeah.
And there's not much happening at the triclinic transition?
No, I don't see much.
This is very different than what we observed, what's in our paper.
Okay.
In our paper, we see you know, similar to the red data you're showing here, but it's a continuous increase to the triclinic transition.
Did you? Yeah. But so what we checked, we measure upon cooling and warming to be sure that there is no hysteresis. Okay. We don't see any hysteretic behavior. And we need also to take in super close. And especially if you measure upon warming, the difference, the temperature difference between the triclinic phase and the orthorhombic phase is even smaller.
Mm-hmm.
I mean, okay, it's interesting. I mean, I'm shocked that there is not a dramatic feature at the triclinic distortion.
If you really look deeply, you see a small feature, but not that much. Actually, if you look in, so I will show after the phosphorus doped compound, and in the doped compound, you can see more feature at the triclinic transition, which is far away from the orthorhombic one.
Yeah, but JP, I mean, I thought I asked you this question when you gave your talk, right? I mean, the triclinic transition is the first order phase transition. You would not expect any sort of you know, the critical regime when you have a strongly first order phase transition.
Sure, but
I mean,
I'm just saying this is what we observed.
The data is data. Yeah, well, yeah, I agree. The data is data, right?
I mean, I can. Yeah.
How strongly first order is the
There's a very sharp heat capacity anomaly.
Yeah, it's very clearly first order. I mean, you know, so I mean, there's many things you could say about it, but below this triclinic transition, you know, the susceptibility doesn't mean anything anymore. It's a different, you know, it's not
sure.
different symmetry.
Yeah.
But we clearly see a very sharp feature at this.
Also in the B1G geometry?
Yeah.
Well, you know, I would say the data looks very similar, except that for us, there's a continuous rise up to 135 Kelvin, and then there's a sharp drop. So I'm very curious why there's a difference, but
okay, you should just continue. Yeah.
I continue. Maybe we can
Thank you.
continue discussing at the end. So I was about now to compare this M12 minus M11 elastoresistance coefficient with the intensity of the incommensurate challenge wave. So which is shown as this Planck square, and you see that these two quantities peaks at different temperatures. Okay, but the onset of the elastoresistance and the strong increase in this intensity occurs really at close temperature. And I will come back to this point again when I show the doped samples. So now I would just like to mention recent inelastic X-ray scattering paper in this undoped BaNi2 that looked at the soft funnel associated with the formation of the incommensurate charge wave. I think they are really nice. So the first one I would like to mention is this one from Michaela Suyu at our institute. And among different things, what they showed is that if you look to the correlation length of the fluctuations of this incommensurate charge wave along the z-axis, you see that it diverges at a temperature which is the orthorhombic transition temperature, or very close to it. So it's within 1-2 Kelvin, something like that. Second thing I would like to mention is also this nice preprint by the group of Birgeneau in Berkeley. And what they have seen actually, still using IXS, is that the formation of this incommensurate charge wave is a two-step process. So first, there is a complete phone softening, and then you have a quasi-elastic incommensurate charge wave fluctuation that slow down to form the charge wave order. So these two studies, together with the elastoresistance, suggest to me that this B1G elastoresistance could be related to this slowing down of this quasi-static, quasi-elastic incommensurate charge wave fluctuations. Okay, that's something that we need to investigate. How it evolves, how this picture evolved with phosphorus substitution. Okay, so now let's go to the phosphorus substituted sample. So I already discussed this undoped compound, and I will show you now 3.5% of phosphorus doping, 7.5, and 10%. And for this last one, as you can see, there is no more orthorhombic structure or triclinic structure. Okay, so we are across the triclinic critical point, and there is a 3 Kelvin or something like that, a bit more than 3 Kelvin TC. So this is the evolution of this B1G elastoresistance coefficient with phosphorus content. So this is plotted as a function of temperature minus the triclinic transition temperature. Okay. So the circles are the elastoresistance coefficient, and the squares are the intensity of the incommensurate charge wave. And what you can see is that for up to 7.5%, what we observe is that this maximum of the B1G elastoresistance broadens with phosphorus content, but it always occurs slightly above the triclinic transition temperature. And what we can notice also is that the onset of this elastoresistance always coincide with a strong increase in the intensity of the incommensurate charge wave. So now let's have a look to what happened at 10%. So at 10%, you see that we still have a broad maximum of the elastoresistance at a temperature close to 50 Kelvin. And the onset of the elastoresistance still coincide with a strong enhancement of the intensity of the incommensurate charge wave. Okay. So we can complete our phase diagram. So that's the T star temperature of the maximum elastoresistance, and you see how it goes in the phase diagram. And what you can notice is that so it follows quite well the orthorhombic transition temperature as inferred by thermal expansion measurement. But at 10%, we still have a maximum, even though there is no more orthorhombic or triclinic structure that has been seen there. Okay, so that's very surprising, and I will come back in more detail about this in the last minutes. But before that, I would like to show you the one thing I already talked about in the undoped compound, which is this hysteretic behavior. So as you can see, we see this hysteretic behavior in the undoped compound. So that's resistance versus strain. But we also observe it in the 3.5% dope sample, 7.5%. But 10%, we don't see any hysteresis. So that does not mean that there is no hysteresis. That means that at least we don't resolve it. So if there is one, it has to be smaller than the experimental noise that we have. Okay. So we can also have a look to the temperature and doping dependence of this hysteretic behavior. And to do that, we plot the hysteresis width, which is defined like that. So that's the maximum width of the resistance versus strain variation you see at a given strain. And so that's the definition, the way to quantify this this hysteretic behavior, which was also used in the strontium dope sample. So what you can see is that we observe that there is a strong enhancement of this hysteresis width, sorry, across the T star temperature, the maximum of elastoresistance, up to 7.5%. But at 10%, we don't see any finite hysteresis anymore when there is no orthorhombic domain. So what it suggests is that at least partially, it could be due to the pinning of orthorhombic domains. Okay, so now I would like in the last minutes I have to take a closer look at this 10% sample, which I think is very interesting. So the first thing I would like to mention is that this sample is actually interesting because it has a nice similarities and differences with this 75 strontium doped sample, which was studied by Jean-Pierre Paglione and co-workers. So the similarity is that in the strontium doped sample, you also have a maximum of elastoresistance close to 25 Kelvin in the absence of a known phase transition. So there is no triclinic phase anymore at this doping in particular. The difference is that in the strontium doped sample, there is this nice Curie-Weiss temperature dependence, which is not observed in the phosphorus doped sample. Okay, so Christophe Meingast has done more measurement on this 10% barium nickel arsenide doped with phosphorus. So you can see the Young modulus along the 100 axis in gray and along the 110 axis in blue. And what you can notice is that there is a lattice softening, but which is observed along both directions and with quite the same amplitude. So that's quite different, for example, to what was observed in barium iron 2 arsenic 2, where you see the softening is much more pronounced along the 110 axis because it's dominated by this C66 elastic constant, which is the soft mode of the transition. So in the nickel case, in this 10% barium nickel arsenide phosphorus, it seems to be more complicated. You can also compare this with this cobalt doped barium iron arsenide, and you see that the temperature dependence is quite different between this critical nematic barium iron arsenide doped with cobalt and in particular with this 100 Young modulus in the nickel compound. Okay. But one thing which I find very interesting is actually to compare this Young modulus data along 100 again with the elastoresistance, and you see that both have kind of the same temperature dependence. So they both, so the lattice softening that you see is associated with a rise of the elastoresistance, and the saturation of the lattice softening is associated to the decrease of the elastoresistance. So that's something we are still investigating. So last thing I would like to mention, I think, is additional thermal expansion measurement in this sample. So you can see the thermal expansion along the 100 axis in red, along the C axis in blue, and you see that there is a clear first order transition, which was seen by high resolution thermal expansion close to 50 Kelvin. Okay. So we are still investigating what it is about. Actually, we still don't know exactly. So I've looked deeply to the in-plane transport and elastotransport, and you see that in transport and elastotransport there is no evidence for any hysteresis. So it's likely not to be this transition is likely not to be directly related to this maximum of the elastoresistance, but we are still working on it. And this leads me to my conclusion with this color map phase diagram. So temperature as a function of phosphorus substitution. And what you can see is that we observe a strong B1G elastoresistance that onset together with the incommensurate challenge wave phase, which suggests that this phase is not a fully biaxial symmetric state. That's also what was suggested by the recent inelastic X-ray scattering works. The temperature dependence of the elastoresistance is quite different from the iron pnictide in this phosphorus-doped barium nickel arsenide, and in particular, it's not Curie-wise. And what you can see is that the strength of the B1G elastoresistance actually decrease with phosphorus substitution, which suggests that the strength sensitive electronic correlation that we probe are not responsible for the high TC or the 3 Kelvin TC on the high phosphorus side. And with that, I would like to thank you for your attention.
Yeah, very nice results. Yeah, I really enjoy your talk. Yeah. So one question I have, can you show your phase diagram again?
Yes.
Yeah, just the one that you just passed. So the question, one question I have is that what is the relationship between the orthorhombic lattice distortion seen by you guys and the charge ordering that's seen by X-ray? I mean, I guess the X-ray people, I ask the structure has not been solved, right? This X-ray structure. Peter Abernathy told me the detailed atomic position is not known.
Yeah.
But when you say you have this orthorhombic lattice distortion, what's the relationship? What's the relationship of that with with the or maybe Matsu is here. He can answer that question. Maybe asking the wrong person.
He's the expert.
I mean, Mehdi knows the answer, of course, but I can just comment on that because we've been looking at this very closely from
right. I was just curious. So,
Again, what happens is that you do have the CW fluctuations, right, which are a fairly short range from room temperature, and the correlation length increase as you decrease the temperature, and then you see the long range CW order that forms just at the temperature which is just above that at which the orthorhombic transition is seen. So we literally have like 1 or 2 Kelvin difference between the temperature at which we see a feature which we can call a Bragg peak, which is really resolution limited and shooting up in intensity, and 2 Kelvin below we see the small distortion in the expansion. And we also see it in the X-rays. I mean, as a broad, I showed that in my talk. Actually, there's a broadening and there's this kind of splitting of the high index peaks. But I mean, Michel has been doing a full refinement of the structure in the orthorhombic phase using the orthorhombic setting. Yeah, I think the storyline is that the CW fluctuations, I mean, they kind of condensate, and when the long range order forms just after, then there is a small distortion that is occurring.
I see. So one can say almost simultaneously or strongly coupled, right? That's a fair statement.
Yeah. That's really good.
Yeah, thank you. Yeah. Any other question?
I had a quick question for slide 20.
Yes.
So your resistivity data, and I think it's slide 20, showed the transition for the orthorhombic state on the piezo stack with no applied voltage in like 2 different directions.
Yeah.
Slide 20.
Sorry.
Yeah. So here you have what looks like a kink at what you're calling the T orthorhombic phase, and this is while it's on the piezo stack with no applied voltage, correct?
Yes, that's correct.
So what is different about this scenario versus when you just measure it regularly with no piezo stack, because that kink is not seen there?
So in the ordered state, so when you are in the tetragonal state, the resistance anisotropy that you can observe should be only due to the strain that you apply. But within the orthomic state, it could be different actually. And if you apply a small strain or a small stress, you can have a large resistance anisotropy, which give you really a too large elastoresistance coefficient that you don't have experimentally. So we should be able to compare, but only when the system is in the tetragonal state. Yeah.
Okay, so is the reason why this is different from a traditional just regular measurement is because it's sitting on the piezostat, which is applying some strain even with no applied voltage?
Yeah, so I think what is happening is that you have some orthomic domains, which I think is also partially at least why we observe this hysteretic behavior, and applying in fact when you glue it to the piezo, you partially detwin the sample. That's
okay,
probably what is happening. So that's what I think is happening. But,
got it. Okay, thank you.
Yeah, I have one more question. Do you have any speculation on the microscopic origin of the orthorhombic structural transition?
I don't know.
I mean, any speculation at all? I mean, because in necktie it's due to magnetic order, right? The coupled magnetic order with magnetism, but since there's no magnetism here.
No, so actually, if you have a look to the paper of Christoph Mangas, what he sees that develops well above this.
Masu's paper, right? The Bama, yeah, okay.
Yeah, and so what is really unusual already from high temperature is the thermal expansion along the c-axis. So there is a large effect along the c-axis, which seems to drive all the physics at high temperature. But what it really means, I cannot say. I don't know.
Thank you. Yeah.
I have a question.
Yeah.
So maybe a bit annoying from theorists, but do the materials exist at the higher phosphorus doping side?
I think there is a problem from the crystal growth side. So if you look, actually, I think it's difficult to grow crystals above 12% of phosphorus doping or something like that.
But so that's a bit problematic for what I wanted to ask. In the ion-based cases, you have these enhancement of the elastoresistability that's accompanied by many other things that's happening, especially in the phosphorus dope cases like mass enhancement and linear T resistivity and so on and so forth. So is there any sign of fluctuation effects coming from other measurements? Because the low doping side, to me, there are too many things happening. So in principle,
yeah. So I think in the Christoph Mangas, one of the messages is that there is a very large fluctuation regime above all this transition, and especially above the orthomic condition. So there is the behavior of the lattice constant along the c-axis and along the a-axis is really anomalous, which probably come from some kind of fluctuation regime that already starts at room temperature, and you have already this transverse optical phonon softening, which occurs at very high temperature, up to room temperature actually. So I mean, it's very a gradual change.
Thank you, KP.
Yeah, thank you.
Hi, yeah, I have a couple comments and a question.
Yeah.
So first of all, about the c-axis role, I believed for a long time, and I think I said in my talk that this system, the arsenic dimer, the arsenic interaction is very strong, just like in the iron compounds, and that there is a similar evolution as you start to play with this structure. So either with phosphorus or strontium, you bring these arsenic ions closer together, and I think it's just a much subtler transition, but I think it's there. And I think this plays some role, and I don't know exactly how, but it certainly plays a role in how these phase diagrams evolve. The other comment was about the phosphorus substitution. It is true, right, that you can make the pure phosphorus compound?
Yeah, actually
that is a 3 Kelvin superconductor?
Yes, exactly, yeah.
Okay, so, I don't know. It's interesting that the 3 Kelvin superconductivity suddenly jumps, but there's not much change through the phase diagram through that regime.
Yeah, I think that's really the main difference with what you have done with strontium. I mean, what we have above the suppression of the tricking phase is really a flat TC compared to what you have.
But what about so my question is about the nematic susceptibility magnitude. How does it change through that region? Is it also not changing?
I can show you maybe. Do I have something? So really, so there is one thing which is still, I think I don't really understand it, is that there is a maximum close to 3.5%. So there is still a tricking phase there. But what we see is that the elastoresistance is larger at some intermediate doping, and then it weakens continuously. Actually. Okay. But that was something that I was wondering for a long time, because I think in the strontium dose sample you also observe a maximum of the elastoresistance at some intermediate doping. So I was just wondering whether it's something we should really take a look at closely, or.
I think the only time we see a maximum that doesn't coincide with the triclinic transition is once the triclinic phase is gone.
Okay.
So as I said before, seems to be a big difference, especially in the x=0 between our data set and yours.
In terms of temperature, how many degrees? I mean, the potentially are different between these.
In the end-up compound, again, that's I don't know, 5 Kelvin maybe, something like that.
Kelvin, okay. Could that be sensor differences, JP?
I'm sorry?
Could that be a temperature sensor differences? I mean,
no.
I mean, I don't think so. I think 5 Kelvin is a huge difference.
It's 7 Kelvin on cooling and 5 on warming. And to be honest, I mean, we looked really at the very same crystal with X-rays, with all our things. So yeah, I really don't know what to say. I mean, from our side, I think it's
yeah, it makes me want to redo the measurement again, but we did it many times.
So I'm just showing you now what we got at 7.5%. So you see, you have the resistance, which is measured on the piezo, and like this downturn is really the transition, and the maximum of the elastoresistance is close to 80 Kelvin. So it's when you increase phosphorus doping, the difference is really larger. I mean,
30 Kelvin.
So in fact, what would be interesting is, I think, is to have a look to this orthorhombic distortion in the high strontium doped sample close to the suppression of the tricking phase. That would be something interesting, if there is any.
Okay.
I had one more question, if you don't.
Go ahead.
Yes.
It's regarding the hysteresis. So our original conclusion was that the nematic susceptibility hysteresis was an indication of nematic ordering.
Yeah.
And I just wonder what your comment is on that, because that we showed a direct correlation between that hysteresis width and the incommensurate charge order.
Yeah. But in the end-up compound, I think I can do the kind of same conclusion. So in the end-up compound, I think we see the same thing. The hysteresis onset with the increase of the intensity of the incommensurate charge wave. Now in the doped phosphorus compound, I see an hysteresis, a finite hysteresis that develops when the intensity is already substantial, I would say, of the incommensurate challenge wave. But I mean, this quantity is not super easy to extract, and in particular, you to observe a finite hysteresis, you need but the hysteresis is above the experimental noise, which depend from sample to sample. So that's difficult to make a conclusion. So the thing that we observe is that this hysteresis clearly increased strongly across the maximum of the elastoresistance. That's what we observe.
But okay, so the clear observation is that the hysteresis is only present when you have incommensurate charge order, right?
But no, because in this 10% sample, we don't observe any hysteresis, but there is still the incommensurate challenge wave. But again, I don't observe it, but does not mean that it's not there. And especially in this 10% sample, everything is at low temperature, and at low temperature, you can only apply small strain. The resistance is small, so the experimental noise, the signal to noise ratio is smaller, so it makes everything more complicated.
Okay,
yeah, just to take advantage of all the expertise here, has there been any RPES measurement of the anisotropy?
Oh, you mean below the CDW?
Or wherever
whatever
these,
orthorhombic, yeah.
These in the parent compound or everywhere else.
I think Ming does a measurement, yeah.
But are the orbitals doing what they're supposed to do?
I'm sorry, your question is about ARPA's signature of the charge order?
Well, just where you have these nematic fluctuations, whether the XZ versus YZ orbitals are having different energies or not.
I think she left. I mean, she would have.
No, I'm here. I'm here.
Sorry.
So,
sorry.
We only see changes across at the clinic transition. We don't observe any significant shift above the clinic transition. Yeah.
I see.
So we only look at the parent compound. That's the.
You look at the dope ones. Yeah.
Okay, so that adds one more mystery to the mix. Thanks.
Yes, it's a great talk. I mean, yeah, it's very, very. Oh, there's one more question online saying, how do you define zero strain of the sample? This is from Zhaoyu Liu from I guess UW. Yeah.
That's a good question. We cannot define the zero strain state in this experiment. So we can try to estimate it from the thermal expansion of the piezo, but it's a difficult thing to do, especially just by gluing the sample to the piezo. You apply a bit of strain just by the drying of the glue, actually. So it's what is important is that the resistance versus strain sweeps are still linear, so you are still in the linear response.
Okay,
that's the important part. Yeah.
So I guess the some part of the question is it close to true zero strain point during the measurement?
Sorry, say it again.
Is it close to true zero strain point during the measurement?
Close, yes. It depends how you define this close. So I can show again the thermal expansion of the piezo.
It's pretty good, right? Yeah.
Okay. So that's the strain state that we can estimate for barium nickel 2 arsenic 2. So you see that we apply. So that's really the maximum strain we could apply if all the deformation was transmitted from room temperature, and we had 100% strain transmission, which is not the case. So that's really upper limit, I would say.
Yeah, very, very interesting result. Yeah, thank you very much. Yeah, I think this material, is worthy of more investigation. Seriously. Yeah, we're trying to work on it. Yeah, thank you. Yeah,
thanks.
Yeah, thank you, Matthew. Yeah, thank you.
Thanks. Very nice talk, Mehdi.
Yeah. Thanks, Mehdi. Yeah. Bye.
Bye.
Thank you all.